Today I have a pretty much completed schematic for my avionics board for my CubeSat, along with a bill of materials and price. I don't yet have a layout, but that is coming next. Remember that this avionics board will roughly end up being 9 by 9 centimeters, and I'm thinking it'll be a 2-layer board just for cost. Interjecting real quick, I realize I go into a lot of detail about the avionics board without really giving an overview of what the purpose of this board is. Its main purposes are attitude control, dealing with radios, command and control of the rest of the CubeSat, and also persistent data storage. So specifically for attitude control, it has a variety of sensors. It has a gyroscope, a sun sensor, a magnetic field sensor, and then it also has a coil driver. This is for attitude control via a magnetorquer. So this is magnetic fields acting against Earth's magnetic field and able to produce a torque and able to rotate the CubeSat into a desired orientation. Maybe it's to de-spin the CubeSat, or maybe it's to point it in a specific direction. As for radio, the avionics board deals with communications with the Iridium satellites using an Iridium modem to talk to the Iridium constellation of low Earth orbit satellites. This makes the assumption that this CubeSat would be underneath the Iridium satellites. Otherwise, it doesn't work. Also, it has a GPS device which it talks to in order to get information about where it is and time information as well. As for command and control, the avionics board has a UART and a CAN communication bus which go off-board. The purpose of this is to command and control other off-board components. In addition, there's temperature monitoring of the other components on the CubeSat. It keeps a real-time clock and keeps track of a schedule of any actions that would need to be performed. And finally, the avionics board deals with persistent data storage, so that's done using an SD card and the MRAM. MRAM being a memory that is specifically resistant to data corruption. And here are some electrical considerations I had in mind while designing this schematic, other than low cost, of course. I wanted every part to have a high temperature range, -40°C to +85°C at least. I wanted a higher voltage rating on all capacitors, and I wanted static protection when possible. With regard to buses, ideally, I wanted one component or one sensor per communication bus, and this just helps to avoid bus lockups where one component can take down an entire communication bus by shorting the lines together or otherwise doing something bad. So specifically, I avoided I2C whenever possible. I just haven't had great history with that communication protocol in the past, and I prefer SPI. In addition, on the board you'll see a lot of just debugging features. There's going to be a lot of test points, and I have a lot of 0 ohm or near 0 ohm resistors which can be useful in debugging to either isolate a circuit and disconnect it, or as a place to put a current probe. In addition, you'll see for all the different devices I have, everyone is on an individual power rail. This is so that each power rail and each device can be individually enabled. Also, one short would not take down an entire system. Anyway, back to the video. At the heart of this board is the STM32 L4 series microcontroller. I selected this for its ease of use, low price, and it has a wide temperature range. And it has large community support as well. I developed this schematic using KiCad, using hierarchical symbols. So I'll just go around the circle here, going over each hierarchical symbol, and then we'll go into more detail in a minute. So we have a temperature sensor with a whole bunch of different inputs. I'm just using an NTC thermistor, so I have a total of 8 different thermistors right now set up. I have a magnetometer using a SPI bus. I have a gyroscope also using a SPI bus. I have my planned sun sensor, which I'll talk about a little bit more and maybe some of the problems with it. I have an attitude control system, which is PWM, pulse width modulation driven. And I also have the debug and just general debug information programming port stuff down here. This avionics board is going to be designed to sit on top of or underneath a power module, and of course this would be able to connect to more boards. A lot of the pins I've reserved for power. Some I have for a UART and a CAN bus. However, I have a lot of unknown pins at this point. I have my GPS. I also have the Iridium connector selected as well. I'm planning to use an SD card and MRAM, which is supposed to be especially resistant to the radiation that you would experience in space. Looking closer at the L4 chip itself, other than some bypass and supporting capacitors here, I have an external hardware watchdog. I have a 10 megahertz temperature compensated crystal that inputs to this chip, which I'll determine later if I actually need it. I just wanted to spec one in case I do. I have a CAN transceiver here. Since printing out the schematic, I've actually connected the power line to the inner board connector over here using one of the spare pins. And then I also have a low power 32 kilohertz temperature compensated crystal down here, which is hooked up directly to the STM's power. This is supposed to be on all the time, and this will be the source of a real-time clock. Looking at the MRAM, here I've selected the MR25H40, which actually I have changed from the 40 to the 10, and this is the 1 megabit version as compared to the 4 megabit version. The reason that I did this was because I wanted to use the AEC Q100 rated part, which would be the part that had a negative 40 to 125 degrees C rating. However, the 4 megabit part was about $30. The 1 megabit part that is rated for the negative 40 to 125 degree C condition was only $8. So until I find out that I need 4 megabits of data of non-volatile memory, I will just end up using the 1 megabit version simply because it saves me $20. Otherwise, this chip is connected to the quad SPI bus of the STM32 microcontroller, and hopefully, with just some software, it works pretty easily. Moving on, let's look at the SD card. So this is a pretty standard part. Since printing, I have actually switched to a different part, to a Molex latching SD card connector instead of a push-pull mechanism. I have the standard pull-ups for all the SD data lines and command lines, but otherwise this is a pretty standard part. Moving on, let's take a look at the external watchdog. I have this TPL5010 selected. I've put a dip switch in the middle of the reset line that it controls, simply so I don't have to deal with, during development, simply disable this functionality altogether. You program the timeout. I'm using this resistor here, and as of right now I've selected roughly 5 seconds for my timeout. Also, a manual reset button up here, which would be especially useful during development. Otherwise, this is a pretty simple part that just ends up controlling the N reset line of the STM32. Now let's talk about GPS and how I am indecisive. The space-rated part that I have talked about previously, the Venus series part, costs around $150 and is a BGA part, which at this time is too expensive for me, and I need to verify that my software can actually talk to GPS, to any GPS, before I go ahead and install a $150 part that may or may not actually work. So I've spec'd out 2 different SparkFun parts that I'll be able to plug into this board. And my plan for GPS all along was to put it on a separate board, so I would connectorize it and just connect to it and not have it on this main avionics board, simply because of RF considerations and how I would want to make just a smaller board more RF complicated instead of making this avionics board more difficult for layout. Now let's talk about the sun sensor and what I have planned for it on this board. So the idea that I was having for the sun sensor was to use this MLX 75306 part. And this is a pretty great part because it is negative 40 to 125 degrees C. It is a linear array of pixels, so the chip itself looks like this. It has an inset array of 128 solar cells or solar diodes that I can read off their intensity essentially using a SPI bus. And the way that I had planned on using this part was, if you can imagine that this is a slit with a single bar across it, and you are shining light down into it. So this would be the sun up here shining light down. You end up with a pattern of light, depending on if your sun is over here or if it's over here, the shadow pattern that this guy leaves, say it leaves a shadow like this, it shines down into the sensor, and you can tell which part is dark and which part is light because I have this fine granularity here. The problem with this part is that while I can buy it right now, it looks like it's obsolete. There are other parts like it, but they don't have this temperature range, and this part is about $20 or $15 or $20 per chip, which is pretty expensive for what I'm trying to do, because this configuration here only gives me one axis of orientation information, so I would need at least two to get two axes of information, and I'm selecting a part that's already obsolete, and I don't know, I just don't really like this option. So what I've done is I've only spec'd out one of these chips, and otherwise I've just left connectors for other off-board chips, since I figure that this MLX part would not actually live on this avionics board. It would live off-board and I would wire to it. However, I'm trying to come up with a solution where I either use other just discrete photodiodes and come up with some other similar situation where maybe I just have 8 photodiodes. I have discrete photodiodes here that detect the light. However, then I have to build the interface to these. I have to read them off and come up with the information that way, probably in an interface that isn't a SPI interface and that requires more pins, and I don't have those pins for that capability. Maybe it requires another microcontroller and then becomes more expensive than this solution in the beginning. So I'm going to need to get creative. Maybe this isn't as good as I thought it would be. Maybe I end up removing it. Not sure at this point. Let's talk about the attitude control system. So for the attitude control system, I am planning on using these DRV chips from TI. I've used 3 of them, one for the X, one for the Y, and one for the Z axis. Other than the power inputs, you'll see that I have three control pins here, which are covered in this table. The sleep pin just simply decides if the chip is on or off. The phase determines if I'm going either the reverse or the forward direction, and the enable, either if it's high or if it's low, is if this chip is either outputting something or not outputting anything. This is easy for me to control from the microprocessor because so the phase is just another pin that selects the polarity, and then the enable is my PWM pulse width modulation signal, which determines if it is either on or off. So getting back to these chips, you'll see that I have a connector here. My intention is that I will hook up some sort of big inductor coil here for each axis, and this would allow the satellite to act against the Earth's magnetic field by controlling these coils and by creating a magnetic moment that opposes the Earth's, thus correcting its orientation. So here is the debug UART, debug LEDs, and the SWD JTAG programmer for the STM32. As of printing this out, I have actually moved away from this big 20-pin connector, and I have just gone down to a 5-pin connector that connects to the SW clock, the SWD IO, and SWO pins. I thought that this connector, to have this on the board, didn't really make much sense. Otherwise, I just have a little debug UART here which connects to a pin header, a 4-pin pin header. So a UART RX and a UART TX, and along with some static protection as well. And then otherwise I just have some LEDs, but just some helpful stuff during debugging. We have a couple ones that we can go over pretty quick. The 32 kilohertz temperature compensated clock. This one's pretty simple. It's just a clock that I have power inputs to. There's an enable pin, a ground, and the actual output signal. These resistors are just if I want to remove these signals from directly connecting to the STM32, just gives me some flexibility. Moving on to the 10 megahertz, we have pretty much the exact same thing, except this outputs at 10 megahertz. So again, an operational enable pin, power pin, an output, and a ground. Again, with the resistors, just for flexibility during development. Here's the magnetic sensor that I am using, the MMC5983MA. You'll see that I had actually selected the MMC 588. However, the 588 part is in very low quantity, so I decided it didn't really make much sense to use that part. Also, the 598 is cheaper. What I really like about this part, other than the fact that it is very easy to communicate with using SPI, is that it has this built-in, so this cap pin, and then this is a ground pin here. It has an internal degaussing function. So while sensing on the X, Y, and Z axes, it can clear itself of any DC bias by using this built-in degaussing function, which is, I think, very, very useful. Well, I hope that it ends up being very useful. And here are the temperature sensors. Again, I'm using a hierarchical sheet in KiCad. All of these different out signals, which are just analog DC voltages, which will get fed into the STM32's analog to digital converters. I've just hooked these up to hierarchical sheets so I could just copy the symbol around. And the actual NTC itself is pretty dang simple. I simply have I have the voltage coming in this case it's at 3.3 volts. Essentially it's a resistor divider between a 47 kilo ohm resistor and a 47 kilo ohm at 25 degrees Celsius NTC thermistor, and ground is connected here. So this thermistor is actually a leaded part. This part actually presents just two holes, which I would wire up a thermistor to. The thermistor that I've selected comes with leads, and I would attach it to some other component. Here we have the CAN transceiver. This is the SN65H, which is a pretty standard part from TI. You'll see that I have the inputs from the STM microcontroller here, the TX and the RX, and they go into this chip here. I have these resistors in the case that I've actually messed up the polarity of these two, and I can hot wire a connection here to here and make it work. This part has the outputs, the CAN H and the CAN L here. Otherwise, you'll see this is some static protection, this NUP chip. Here we have the Iridium 9603N interface. So the way that I interface with this chip is through this 20-pin connector here. Really, it's as simple as just hooking up all the required pins to their selected spots. The ones that I'm primarily interested in are the DFTX and DFRX. I'm pretty sure that these are other than the power and the on and off switches, this is the minimum of what you need to actually make this thing work. Otherwise, it has a modem interface with all these dataset ready, clear to send, CTS, RS, and the ring, and the data terminal ready signals. These just make up a proper modem interface, which is useful, and I will try to implement it and use it. But really, all that really matters is the TX and RX pins, which I have hooked up on this Samtech connector. And the final page of my schematic is this. It was the i3G 3-axis gyroscope, but it is still a gyroscope. I'd initially selected this i3G4 part, but it ends up that there's not many in stock, and it's more expensive. In addition, the alternative that I found, the BMG 250 by Bosch, is a lower power device, and it is also smaller. So this is what I've ended up going with. However, most of the connections stay pretty much the same, other than that this PLL filter go by the wayside. Anyway, that's pretty much the entire schematic. Only thing I forgot to mention is that everything is going to be running off of 3.3 volts because I found that all the components I've selected, everything works with that voltage. I don't need a different I/O voltage. I don't need any sort of logic level translators, though I could use those to help isolate different buses. If I find out that certain parts are more likely to fail than others, those provide a good level of protection. But at this point, for low cost, everything runs on 3.3 volts, makes my life simple. Also, I've selected all the different capacitors on the board are at least 10 volts or higher compliant. I wanted to make sure everything was at least rated for 10 volts. And in addition, everything on this board is at least -40 to plus 85 degrees C, temperature rated. Every part that I could find that went to plus 125 degrees C I picked. So like this STM part goes up that high. A lot of the other parts on this board are rated for that higher temperature, which I figure is necessary for a CubeSat. Oh, and one last thing. Everything on this board, all the different parts, all the different sensors, the microcontroller, everything adds up to just under $90. Getting a PCB made for this board, I'm aiming for a 2-layer PCB. I'll go with a cheap overseas manufacturer, so I'll probably end up with maybe $50 for a couple PCBs. So far the budget is looking pretty good. This Avionics board is about as much as I expected it would be, just in terms of parts. And if I wanted to get a higher quality PCB, then this would go up. Anyway, in my next video I plan on either talking about the schematic for the EPS, electrical power system, schematic, or I will be reviewing the layout for this Avionics board, whatever I end up feeling like doing next. Anyway, thanks for watching.